Hi, I'm Russ Klein, and I'm a program director with Mentor Graphics, Siemens business. I work in the high-level synthesis group called Catapult, and I'm going to be talking today about developing an ARM coprocessor using high-level synthesis. Here's an agenda of what I'm going to be going over today. Starting with what is high-level synthesis. I'll briefly talk about what high-level synthesis is and how we'll use it to generate a block of hardware. Then I'll be talking about the SHA-256 hashing algorithm. This is the algorithm that we're going to be using to implement as a coprocessor. So we'll talk about synthesizing that algorithm into a coprocessor and connecting it up to the ARM Corstone IoT platform. This is ARM's embedded IoT platform, which is used as a starting point for many embedded designs. It has the Cortex M33 processor in it, which introduces a new coprocessor interface. And I'll be talking about the hardware connection for that particular processor. And I'll also talk about how to program that coprocessor within the context of the Corstone platform. And finally, I'll talk about the power, performance, and area comparing just running software on the ARM processor versus running the full algorithm using the coprocessor that we've created with high-level synthesis. So traditionally, when you're building a block of hardware, you would use a hardware description language at the register transfer level, or RTL. This would be Verilog or VHDL. And at a very low level, you would describe the hardware that you're constructing. High-level synthesis uses a much more abstract C, C++, or System C description of an algorithm, and uses that to create the RTL description of the hardware to be built through a compilation process. And this brings a number of benefits to the developer. The first is productivity. So traditionally, your productivity is limited by the number of lines of source that you're going to develop. C++ describing the algorithm is going to use somewhere between 10 to 100 times fewer lines for that description than the RTL. And then the RTL can be compiled and will be correct by construction from that functional C description. So there's a really big productivity boost in terms of using a much more abstract description of the function that you're implementing in hardware. The next benefit comes in terms of verification. Verification is typically a much larger and more complex task than the design itself. When using high-level synthesis, we can verify the original C algorithm and then prove equivalence between the C and the RTL that was compiled. And we can do that either formally or dynamically or some combination of the two. But that allows us to speed verification up rather significantly. We have customers that tell us they're saving 90 to 95% of their verification time when they use high-level synthesis. High-level synthesis also allows you to explore architectural alternatives for your hardware much more quickly than you could at the register transfer level. So looking at pipelining things differently, creating a different number of execution units can all be done very quickly, very easily. You can evaluate those results without going through a full implementation process. It also will eliminate the manual RTL coding errors. You're not going to be spending time down at the very low level manipulating RTL code, and therefore those types of errors just disappear, as well as the debug time necessary to go through it. And finally, high-level synthesis gives you independence from your target technology. It can be targeted either at an ASIC or an FPGA. And it does it in a way where we do not have to describe exactly what will end up in combinatorial logic between register stages. That will be a downstream process, part of the compilation. and that makes retargeting the algorithm much easier. Now, high-level synthesis gives you a great deal of control over the microarchitecture of the hardware that you're creating. So as a developer, you have complete control over the parallelism that will be introduced into the design, trading off the throughput area and latency. So as a developer, for example, if you had an array, you could decide whether that array was going to be put into memory or into registers. Registers obviously take up a much larger area in silicon, but they're much faster to access and can be accessed in parallel. Memory is going to be more efficient, but will generally be slower. And this type of exploration is typically done through tool constraints in the high-level synthesis compiler, not by changing the source code. So here we've got a little example code where we've got a multiply accumulate loop. We can run this through the high-level synthesis tool in one of two ways. On one hand, we could create a circuit that had a single multiplier and a single adder, but it would take n clocks to complete the algorithm. We could also unroll the loop completely, having n multipliers running in parallel with n-1 adders to create an adder tree. This is going to run faster, but will be much larger. We could also do some combinations of these two to pick any number of multipliers between 1 and n. And so this gives us the ability to trade off the area, the throughput, and the performance of the circuit that we're generating from that original algorithm without making changes to it. High-level synthesis also gives us independence from the target technology, which means we can retarget it to different platforms very easily. Traditionally, in RTL development, there's a technology penalty for reuse. In other words, if we describe the algorithm for a particular speed of ASIC library, and we now want to use RTL synthesis to try to retarget it to a faster platform, sometimes the RTL synthesis tool can compensate for that, but it's going to spend a lot of time and it won't always be successful. So here we have, again, a simple loop. If we're targeting at a slow FPGA or ASIC implementation, it might break it up into, say, 3 different register stages and perform combinatorial operations between those. And if we're targeting it at a fast ASIC or FPGA technology, we could pack all of the operations into a single clock cycle. And this is done by the high-level synthesis tool before we get to RTL synthesis, which means that we can target different technologies very quickly and easily. And now let's talk about the algorithm that we're going to be targeting to our coprocessor. It's a SHA-256 hashing algorithm. This is a very compute-intensive algorithm, but it operates on relatively small amounts of data, making it ideal for building into a coprocessor. It processes data in blocks of 512 bits. So we start off with an initial hash, and we perform a transform operation on a block of data and that hash. And then we'll pass the resulting hash into the next stage of the transform with the next 512-bit block. And we'll repeat this until we've consumed the entire set of input data. And that will give us our final hash. The SHA-256 algorithm is used in a lot of different encryption operations. It's also used in Bitcoin mining, something that's a lot of people know about. So this diagram kind of gives us some hint as to how the transform works. So the transform is basically going to be taking our A through H, those are 32-bit values, and those 32 bits are then run through a shift operation where each one is shifted over by 32 bits. And the top level bit is run through a set of exclusive ORs, summations, and shifts, and dropped back into the top 32 bits. This is repeated 64 times for a complete iteration of the incoming 512-bit packet that we're going to be hashing on. Now, some things that we can notice about this algorithm is that these shift operations and these bit extraction operations are things that are very easily handled in hardware, but are generally fairly inefficient on traditional CPUs. The other interesting thing to note at this is that this is highly parallelizable. So we have a lot of operations, these addition operations, the shifting operations, the exclusive OR operations, that can all take place in parallel. If we're running it on a traditional CPU, it's going to be a sequential process, which will be fairly slow. Moving it into a hardware block means we can take advantage of the inherent parallelism of hardware. And this gives us a significant speed up by running this in a coprocessor as opposed to traditional software. So to create our coprocessor, what I did was went to a GitHub location that's maintained by the National Institutes of Standards Technologies, and they have the reference algorithm for the SHA-256. Taking that, I made a few minor modifications to it, really on the interfacing. The author of the algorithm would certainly recognize it as a SHA-256 algorithm that they had created. And with those modifications and identifying loops that we were going to unroll and some pipelines that we were going to create in the hardware, I ran it through Mentor's Catapult high-level synthesis tool. And this generated a block of synthesizable Verilog that represented that same function that was described in our algorithm in C++. And so this has the exact same functionality, but now it is at a level where we can feed it to an RTL synthesis compiler for gate level implementation and layout. The original algorithm is about 200 lines of C code, and the resulting Verilog is about 5,000 lines. And I was able to download this, make the appropriate modifications, and generate the RTL implementation in about an hour. So definitely an improvement in developer productivity there. Now, we're going to take this generated Verilog and put it into the ARM Corstone platform. This is ARM's embedded IoT platform. It contains 2 Cortex M33 processors, a number of timers. It's got an AHB5 multi-layer interconnect fabric and several blocks of SRAM for code and data storage. It also has some expansion ports for adding masters and slaves into the design, but we're going to be connecting this up to the CPUs through the coprocessor interface. The ARM coprocessor interface is something that ARM has recently reintroduced to its processor line. The Cortex M33 is the first to receive this new interface. It allows you to add up to 8 tightly coupled computational units to the design, which are accessible over a non-arbitrated bus interface that executes in a single clock. So we can pass data to and from the core of the CPU into the coprocessors very quickly and efficiently. ARM had these originally on the processor lines, the 7-TDMI and the 9-TDMI, prior to the Cortex line. With the Cortex line, these dropped away, so it's good to see them bringing the coprocessor interface back. This is the set of signals that is exported by the ARM Cortex M33 for the coprocessor. This in the IoT platform, it's instantiated in the file named eCPU IoT F1 expansion. And this is where you would instantiate all of any or all coprocessors that you're going to be implementing. The inputs to this module would be driven directly from the M33. The outputs are driven back to the M33 directly. If you're not using the IoT platform, you would see these exact same signals on the M33 processor and could connect up to them in the same way. So to interface to the coprocessor, these are the signals that you'd want to look at for transferring data from the processor registers into the coprocessor. The CP-MCR signal is going to identify that we have an outbound transfer. It's going from the CPU to the coprocessor. The CP size signal tells us how much data we're moving. Are we moving a single register of 32 or two registers of 64? The coprocessor register signal contains an encoding of which coprocessor registers are we writing to, and the CPW data signal contains the data that's going to be written to those registers. So using these signals, we can identify what data goes into the registers and route them to the appropriate coprocessor registers. For a read signal, it's just about the same set of signals. It's very similar. We're going to be looking at the CP-MRC signal, identifying a transfer from the coprocessor back to the CPU. The CP size will be indicating the size of the transfer, one or two registers. The CP regs will indicate which coprocessor registers we're reading from, and the data will end up in the CPR data signals. Now, before we can use the coprocessor, we need to enable it. And enabling it means writing a specific bit pattern to the coprocessor access control register on the Cortex M33. The Cortex M33 has a bank of system control registers that start at 0xe followed by 7 zeros. The coprocessor access control register is located in an offset of ED88. This diagram displays the fields within that register. We're going to be attaching this coprocessor to coprocessor slot 0. If we set the CP0 field to a 0-1, we would get secure access only. Setting it to a 1-1 gives us full access. So this line of C code where we OR in the value 3 to this particular address will turn on that coprocessor and allow coprocessor instructions to access it. There's quite a bit more detail on this in the ARM v8m architectural reference manual. So to program the coprocessor, we're going to be using the assembly language instructions MCR, MRC, MRRC, and MCRR. And these are used to pass data back and forth between the processor and the coprocessor. Now, I wasn't able to find any documentation that directly indicated which fields of the instruction end up on which signals that we looked at just a couple of slides ago. So here's a partial mapping that describes how that works. So the first parameter, P0, that number 0 is going to end up on the signal CP-num, the coprocessor number, bits 2 down to 0. The second field is the opcode, or the operand, that we're going to be passing to the coprocessor. And this is, again, a 3-bit field, and this shows up in the CP-OPC signal. R5, the third parameter, is the CPU register that we'll be reading from. And here, the data that's contained in R5 will be passed to the signal CPW data. CR3 and CR7, the 3 and 7 will be encoded into the CP reg signal. So the first field will end up in bits 3 down to 0, identifying one of the 16 registers in the coprocessor to be written by the low order data in W data. And then the second field, the 7, gets encoded into bits 11 down to 8 of CP reg, and that identifies where the high 32 bits in the CPW data is going to be sent to. Now, assembly language instructions are rather difficult to access from C code. And so we've got a couple of ways of accessing the coprocessor from C code. One of them is using intrinsic functions. And this is part of the ARM C language extensions that are available with almost all the embedded compilers that support the ARM coprocessor extensions. And so these definitions are in a header file called arm_acle.h. And if you include that, you'll get a number of functions which will be inlined, _, arm, and then the name of the instruction, followed by a list of parameters. And here we'll be able to use C variables and call this directly. What goes on in that header file is it ultimately calls that assembly language instruction. There's a lot more information on this documented in the Cortex M33 instruction set reference manual. Look up coprocessor intrinsics. Another way to access it from C code if you're using GCC, and this is the way that I did it, is to use the GCC's assembly directive or ASM directive. And so in your C code, you'd simply use the ASM directive followed by the assembly language instruction that you want to insert. The %0 is a parameterized value where we can put a C variable that will substitute in for that. The compiler then will appropriately go to and place that variable into the appropriate register and create the coprocessor register encoding. So the top instruction is one where we are sending the value foo out to the coprocessor, and the second one is where we're reading in the variable bar. We're going to be writing to the variable bar from a coprocessor register. I generally will wrap these in macros to make them a bit more understandable to the programmer, making usually something more meaningful than set CP, but set CP gives you a feel for how you would pass a register value pair down to the coprocessor. So our coprocessor that we created for running the SHA-256 encryption has this register map. So we have a number of registers 0 through 5 that we can read and write. The reset will do a soft reset on the coprocessor. We have a done bit that will tell us when when the computation is complete, and we have two 64-bit ports, one for passing data in and one for reading the hash out. And so using the macros that I described earlier, this is what a compute hash function would look like, and it would be callable from C within the application that's running on the M33 processor. So we would pass in a pointer to a buffer, an integer count of the number of 32-bit words that we want to pass down to the hashing algorithm, and then a pointer to a buffer where we will return the result of the hash algorithm. There is a problem down here at the bottom. The lower loop is not I less than 32. It's actually I less than 8 for anybody who's paying very close attention to the algorithm there. But that does read out the 256-bit hash that results from the computation. Now, the performance that we were able to achieve, here we looked at how long did it take to compute this SHA-256 hash algorithm, purely running it in software, where we had enabled all the caches, set the compiler optimization flags to run as quickly as possible to maximize performance. And we compared this to doing the exact same computation using the coprocessor accelerator that we created using high-level synthesis. Both the accelerator and the processor are going to be running at the same clock frequency, and we measured the performance in clock operations. The coprocessor is accessed using the MRCC and MCRR instructions, specifically passing 64 bits of data on each transfer. And we ran this against an 80-bit payload, an 800-bit payload, and an 8,000-bit payload. And what we were able to see is that in software for 80 bits, it took almost 3,500 clocks. Using the coprocessor, it was just 391 clocks. For an 8,000-bit payload, it's almost 60,000 clocks in software and just 11,000 clocks in hardware. Now, we also looked at the power and energy consumption for computing the hash. For a lot of embedded systems, more important than performance will be the power or the energy used in a particular computation. So we took the design and targeted at a 14 nanometer ASIC technology running at 0.72 volts. And again, using the same 80, 800, and 8,000 bit payloads, we can see that the power consumed by the system as we added the coprocessor went up a little bit. So without the coprocessor, it was about 13 milliwatts, or microwatts, excuse me. And adding the coprocessor brought that up to 14.5 to 15 microwatts. And if we then compute the energy used to compute this hash, for an 80-bit payload, it's 90 nanojoules without the accelerator. And with the coprocessor, it's just 11 nanojoules. And for our larger payload, it's almost 1,600 nanojoules in software. And using our coprocessor, it's just 343 nanojoules. So a significant energy savings, which translates out into less cooling and longer battery life. This is the area that was taken up by the coprocessor that we created. So the IoT subsystem itself, the Corstone platform, was 285,000 square microns, again, using our 14 nanometer ASIC library process. The coprocessor was 34,000 square microns. So it increased the size of the design by about 15%. In terms of NAND gate equivalents, it's about 1.1 million for the subsystem, and adding about 143,000 NAND gate equivalents to the design for adding the coprocessor. For anyone interested, this is the floor plan of the complete IoT subsystem, the Corstone platform, and the coprocessor that we added to it. So a coprocessor is a method that we can use to significantly improve the performance or improve the power consumption characteristics of a particular algorithm that we want to implement on our system. Here we used high-level synthesis to design and very quickly verify that accelerator. We connected it into the coprocessor interface. That interfacing was really quite straightforward. The signals to address the registers in the coprocessor are really pretty easy to hook up. And we were able to programming in the C code using the intrinsic functions, so calling the hash algorithm from our C application and getting the result back was very straightforward as well. It allowed us to run our SHA-256 hashing algorithm about 7 times faster and use significantly less energy to perform that computation. Using high-level synthesis, we could really target any algorithm that was appropriate for a coprocessor and plug it right into this design quickly and easily. I'd like to thank you for listening to my presentation today. Again, I'm Russ Klein, a program director with the Catapult Group at Mentor Graphics.